This question is about lattice enthalpies. Figure 1 shows a Born-Haber cycle for the formation of magnesium oxide. Complete Figure 1 by writing the missing symbols on the appropriate energy levels. So, we can see that this question is 3 marks, and we have 1, 2, 3 blank energy levels to fill in. That means we're going to have 1 mark per energy level. Now, a Born-Haber cycle shows the different enthalpy changes involved in the formation of an ionic compound from its elements in their standard states. So this jump here represents the overall change in this Born-Haber cycle, which is the enthalpy of formation of magnesium oxide. And to make that overall change, all of these steps here are different enthalpies involved in that overall change. So to begin with, we jump from our elements in their standard states to as gaseous atoms. So these here are enthalpies of atomization. So the first, we are going from half a mole of oxygen molecules to 1 mole of oxygen atoms. And what's important is they're both gaseous here. So this is the enthalpy of atomization for oxygen. Then, this jump here, we're going from 1 mole of solid magnesium atoms to 1 mole of gaseous magnesium atoms. So this is the enthalpy of atomization of magnesium. Now we've reached this point though, we have found our blank energy levels. And we can see that from the start of these to the end of these, the change is that we have gone from gaseous atoms to gaseous ions, so Mg2 plus and O2 minus respectively. So these 3 steps here are going to have to involve the ionization of magnesium and the gaining of electrons for oxygen to form those negative ions. Magnesium needs to be ionized and it needs to lose electrons to form these positive ions. So the first step is going to be ionizing magnesium, so it's going to lose some electrons. And this is the first ionization energy of magnesium. 1 mole of gaseous magnesium atoms loses 1 mole of electrons to form 1 mole of gaseous magnesium ions. So in this case, what we're going to have after this jump is we're going to have 1 mole of gaseous magnesium plus 1 ions, plus 1 mole of electrons that they lost to form those ions, and our oxygen atoms are going to remain unchanged. Then, this second jump here is going to be the second ionization of magnesium, as we need Mg2 plus, so we are going to have a second ionization, which means that our magnesium plus 1 ions are going to lose another mole of electrons to form a mole of Mg2 plus gaseous magnesium ions. We are then going to have now 2 moles of electrons here, because we've just gained another one from the magnesium losing them. And we're going to still have our gaseous oxygen atoms, which are as yet unchanged. However, we are now going to start to see that change, as now our magnesium is ionized as far as it's going to be ionized, as we're not going to go to magnesium 3 plus, it's going to stay at magnesium 2 plus. Our oxygen atoms are now going to start gaining electrons to form negative ions. So this is the first electron affinity of oxygen. And what that means is our 1 mole of oxygen atoms is going to gain 1 of our moles of electrons to form a mole of gaseous O minus ions. So we're going to have our magnesium 2 plus ions still gaseous. We now only have 1 mole of electrons, as 1 of them is being gained by that mole of oxygen atoms, and we're going to have a mole of gaseous O minus ions. From here, that's our 3 marks. The final 2 steps of our Born-Haber cycle are going to be the second electron affinity of oxygen as it gains another mole of electrons to form a mole of 2 minus ions from this just 1 minus ions. Then from up here to down here we have the final step, which is the enthalpy of lattice formation for magnesium oxide when we are going to go from our gaseous component ions to our solid ionic compound. Table 1 contains some thermodynamic data. So the table shows the enthalpy change values in kilojoule per mole for the enthalpy of formation for magnesium oxide, the enthalpy of atomization for magnesium, the first and second ionization energies for magnesium, the bond dissociation enthalpy for oxygen, and the first and second electron affinities for oxygen. And we want to use these to calculate a value for the enthalpy of lattice formation for magnesium oxide. And this question is 3 marks. So, in order to calculate a value for the enthalpy of lattice formation for magnesium oxide from these values, we need to apply Hess's law. Now, Hess's law states that for a given enthalpy change, say A to B, the overall enthalpy change is going to be the same no matter what route we take. So if instead of going straight from A to B, we went first to C, and then from C to B, the overall enthalpy change would be the same. It's an extension of conservation of energy. The idea is it doesn't matter what route we take for a given process, as long as the overall process has been the same, so A to B, then the enthalpy change will also be the same. What this means is we can use it to say that the enthalpy of formation for an ionic compound will be the same as the sum of all the enthalpies involved. So the atomization of all of its component elements, the ionizations and electron affinities for them to form those ions, and then finally the lattice formation to go from those ions to our final compound. So if we were to express this as an equation, what we would see is that the enthalpy of formation for magnesium oxide is equal to, first of all, the enthalpy of atomization for magnesium, and then the enthalpy of atomization for oxygen is a little different in this question. And instead of giving us the enthalpy of atomization for oxygen, it gives us the bond dissociation enthalpy. And what this means is it's about the enthalpy required to break all the bonds in 1 mole of our molecules. And so in this case, it's saying this bond dissociation enthalpy is the enthalpy for breaking every bond in 1 mole of oxygen molecules. So this isn't quite the same as our enthalpy of atomization, as we only have half a mole of oxygen molecules to form our mole of magnesium oxide, as oxygen molecules are O2, and we only need one oxygen atom per molecule of magnesium oxide. So we are actually only going to have half of our bond dissociation enthalpy for oxygen. Then we would have our ionization energies for both our first, which we write as first IE for magnesium, as well as our second, which is written in the same way, but with the second. After this, we are going to have our electron affinities for oxygen. So this is written as delta H first EA, and then like with the others, we put the species in brackets, and then we also have our second written with the same form as the ionization energies. It's the whether first or second, and then our abbreviation. Finally, we would have our lattice formation enthalpy. So that's going to be delta H LF, and this is actually the lattice formation enthalpy for magnesium oxide. So we are going to have MgO as our species. So this long equation here would be our first mark for this question. The second mark we are going to get by substituting in all of the values from table 1 into this equation. So we would need to write this now as minus 602 is equal to 150 plus half of 496 plus our first ionization energy, which is 736, plus our second ionization energy, which is 1450. Then we're going to have our adding our first electron affinity for oxygen. We need to be careful though, because this is a negative value, so that's actually going to be minus 142. Then we're going to add our second electron affinity for oxygen, so this is plus 844. And finally, we have our lattice formation enthalpy, which we don't know, so stays as a more algebraic term, as it was in the previous equation. Now that we have all of our numbers substituted into our equation, we can begin to simplify it down and find our final answer for that third mark. So this so far has been 2 marks, one for this algebraic form, and then the second for substituting in the numbers. And we're going to now simplify this down so we can find our value for lattice formation. So adding all of these numbers together on this side will simplify down to minus 602 is equal to 3,286 plus our lattice formation enthalpy. Then we're going to rearrange this in order to find our lattice formation enthalpy. So rearranging that, we are going to find that we will have, so delta H LF MgO is equal to minus 602 minus 3,286. So our final answer is going to be minus 3,888 kilojoules per mole. Nitrogen and hydrogen were mixed in a 1:3 mole ratio and left to reach equilibrium in a flask at a temperature of 550 Kelvin. The equation for the reaction between nitrogen and hydrogen is shown. We have 1 mole of gaseous nitrogen molecules reacting with 3 moles of gaseous hydrogen molecules in a reversible reaction to form 2 moles of gaseous ammonia molecules. When equilibrium was reached, the total pressure in the flask was 150 kilopascals and the mole fraction of ammonia in the mixture was 0.8. Calculate the partial pressures of each gas in this equilibrium mixture. So we can see that this question is worth 3 marks, and we have 3 partial pressures to calculate. So we're going to have 1 mark per partial pressure that we calculate. Now, to start this question, we need to know how to calculate partial pressure. So the partial pressure of a gas is equal to the total pressure multiplied by the mole fraction of that gas. So to begin with, we already have the total pressure value and the mole fraction of ammonia, so we can immediately calculate the partial pressure of ammonia by simply doing 0.8 multiplied by 150. So this is going to get us a value of 120 kilopascals. So we can fill that in our answer. We don't have the mole fractions for nitrogen or hydrogen though, as we only have the mole fraction for ammonia. However, we can use this to calculate the total mole fraction that the nitrogen and hydrogen take up by doing 1 minus 0.8, which will get us 0.2. the question tells us that nitrogen and hydrogen will mix in a 1:3 mole ratio, and that's the ratio that they react in as well. So that means that nitrogen and hydrogen are going to be in a 1:3 ratio. So what we need to do is split this 0.2 in a 1:3 ratio. So splitting that up, all we're going to need to do is do 0.2 divided by 4, which will get us 0.05. So this is going to be a 0.05, that's the 1, against 0.05 times 3, which will be 0.15. So it'll be 0.05 to 0.15. Now, these will be our mole fractions for nitrogen and hydrogen, respectively. So all we need to do now to calculate the partial pressures for these is to use our equations. So we're going to do, first of all, nitrogen. So we would do 0.05 times 150, which is going to get us 7.5 kilopascals. And for the partial pressure of hydrogen, we are going to do 0.15 times 150 kilopascals to get a total of 22.5 kilopascals. So our third partial pressure is going to be 22.5. So here we now have our three partial pressures, which we will get 1 mark for each. Give an expression for the equilibrium constant Kp for this reaction. So this question is worth 1 mark, which means that we need to get the whole expression right in order to get that mark. So the expression for the equilibrium constant is going to be derived from our reaction equation, which in this case is 1 mole of nitrogen reacting with 3 moles of hydrogen in a reversible reaction to form 2 moles of ammonia. Now, the equilibrium constant in its Kp, in its general form, is the product of the partial pressures of the products, each to their respective molar ratio, divided by the product of the partial pressures of the reactants, again each to their respective molar ratio. So, in the case of this reaction here, we only have the one product. So the upper half of our fraction is simply going to be the partial pressure of ammonia to the power of 2, as that's our molar ratio, 2. However, the lower half of the fraction is going to be, first of all, we're going to have the partial pressure of nitrogen, and we aren't going to raise this to any power as the molar ratio for this is 1, but this is going to be multiplied by the partial pressure of hydrogen to the power of 3, as this is its molar ratio. So this is the full expression that is needed, and all of that will get you the 1 mark. In a different equilibrium mixture under different conditions, the partial pressures of the gases are shown in Table 2. Table 2 shows us that the partial pressure of nitrogen is 1.2 times 10 to the 2, for hydrogen it's 1.5 times 10 to the 2, and for ammonia it's 1.1 times 10 to the 3. Calculate the value of the equilibrium constant Kp for this reaction and give its units. So this question is 2 marks, and we need to give both the value of Kp and its units. So that will be 1 mark for the value of Kp and 1 mark for the unit. To calculate Kp, we need to use the expression that we worked out in the previous parts of this question, which shows us that Kp is equal to the partial pressure of ammonia to the power of 2 over the partial pressure of nitrogen multiplied by the partial pressure of hydrogen to the power of 3. Now that we've got this, we need to, this expression for Kp, we need to substitute in the values given to us in Table 2. So writing that out with those values, we would have 1.1 times 10 to the 3 all squared divided by 1.2 times 10 to the 2 multiplied by 1.5 times 10 to the 2 all cubed. So then plugging this expression into a calculator is going to give a final answer of 2.99 times 10 to the minus 3. This is to 3 significant figures, which is an appropriate level of significance to be working to. So now that we've got this figure, we can write it in our answer. 2.99 times 10 to the minus 3. However, we still need to work out our units, which is a little more complicated than just going to be kilopascals. The way we need to find our units is by substituting into our Kp equation once again, but this time using the units involved in each of these. So each of these partial pressures is measured in kilopascals. So what we will do is write it out once more with kilopascals squared over kilopascals multiplied by kilopascals cubed. We can then start to simplify this down. So we can simplify the bottom of the fraction first. So we're going to have kilopascals squared still on the top. So on the bottom, this kilopascals times kilopascals cubed is going to become kilopascals to the power of 4 as we add the indices when we are multiplying the same unit together. However, now we are dividing these same units, so we are going to subtract the indices. So kilopascal, so squared divided by kilopascals to the 4 is going to be kilopascals to the power of 2 minus 4, which is going to be to the minus 2. So we can write into our answer kilopascals to the minus 2 for our units. So we will have 1 mark for this value and 1 mark for these units. The enthalpy change for this reaction is minus 92 kilojoules per mole. State the effect, if any, of an increase in temperature on the value of Kp for this reaction. Justify your answer. This is worth 3 marks, which means we will have 1 mark for stating the effect on Kp of the increase in temperature, and 2 marks remaining for our justification. With questions like these, it can oftentimes be better to actually ignore the way the question has ordered your answer for you and work out the justification first, as that is actually the reasoning you're going to need to understand in order to be able to actually state the effect on Kp. So the first thing we can notice from this question, and the first step in the reasoning, is going to be that the forward reaction is exothermic, and we can see this from the enthalpy value they've given us. As it is a negative enthalpy value for this reaction, that means that the reaction is losing energy, so it is an exothermic reaction. Now that we've determined the type of reaction, we can begin to talk about what effect the change in juice will have on that type of reaction. And we want to be talking about this in terms of the equilibrium. So in this case, we would find that the equilibrium is going to move left. And the reason for this is that our forward reaction is exothermic. However, endothermic reactions are what are favoured by an increase in temperature, as the endothermic reaction will take in energy. So the forward reaction is exothermic, which means the backwards reaction is endothermic, so it's that backwards reaction that will be favoured. And so it will move, the equilibrium will shift in favour of the backwards reaction, so it will shift to the left. These first 2 points will represent the first mark on our for our justification. So that's 1 out of 2 marks for our justification. The third mark is still for the effect on Kp. For the second mark for our justification, we need to state why the equilibrium will move left, what it's doing as to why it's moving left. So that is going to be an application of Le Chatelier's principle. So we need to state something along the lines of this is to reduce the temperature which opposes the change. We don't have to state Le Chatelier's principle either in words or even mention it by name. The important concept to get the mark is the idea that the shift in equilibrium is there to oppose the change. Now that that idea of opposing the change, or just stating how it would oppose change, so in this case reducing the temperature, but if say it was an increase in pressure, then it would move to reduce the pressure. So we can either say it's just generally opposing the change or specifically stating what it is, but importantly we need to express the idea that it is opposing the change rather than just saying Le Chatelier's principle by name. But now that we have gone through this reasoning, we can work out how this is going to affect Kp. So Kp, like other equilibrium constants, has products over reactants. So in this instance, the equilibrium is moving left, which means that the mole fraction of our products is going to reduce and the mole fraction of our reactants is going to increase. Whenever we have a fraction, an increase in the size of the bottom half, the denominator, and a decrease in the size of the top half, the numerator, is going to decrease the size of the fraction. So this means that the effect on Kp from this increase in temperature is that it is going to lower. So we have 1 mark for stating this effect, 1 mark for these first 2 points. The key point is about the movement of the equilibrium. So just stating the equilibrium will move left would get the mark. However, it's important context to include that the forward direction is exothermic, and that final mark is for including that idea of it's doing this to oppose the change to the equilibrium. The equation for the reaction between ammonia and oxygen is shown. We have 4 moles of ammonia reacting with 5 moles of oxygen in a reversible reaction to form 4 moles of nitrogen monoxide and 6 moles of water. We are told that the enthalpy change for this reaction is minus 905 kilojoules per mole. Some standard entropies are given in Table 3. Table 3 shows us that the entropy for ammonia in its gaseous state is 193 joules per Kelvin per mole. For oxygen, it's 205. For nitrogen monoxide, it is 211. And for water, it is 189. All of these are in their gaseous state. So this entropy here, this 189, is for water vapor, not liquid water. Calculate the entropy change for the reaction between ammonia and oxygen. And this question is worth 2 marks. So as it is a calculation question worth 2 marks, we are going to have 1 mark for showing the method we've used to calculate it, and 1 mark for our final answer. So in order to calculate entropy change, we need to, so the entropy change, represented by delta S, is calculated by the sum of the entropies of the products, subtract the sum of the entropies of the reactants. This finds us the entropy change in a reaction. It is quite literally just the change in entropy from the start of the reaction with the reactants and to the end of that reaction with the products. So all we need to do from here is to add up all the entropies on our products side of the equation. So we'd have 6 lots of 189 and 4 lots of 211, and then subtract all the entropies from this side of the equation. So 5 lots of 205 and 4 lots of 193. So writing that out as our equation, which is what we'd need to do in order to get the marks, we'd start with our products. So we'd have six lots of 189 joules per Kelvin per mole, plus 4 lots of 211 joules per Kelvin per mole, close brackets, subtract 5 lots of 205 joules per Kelvin per mole, plus 4 lots of 193 joules per Kelvin per mole. So we'd need to write this line here in order to get that first mark, as this shows that we have interpreted our equation correctly and substituted in our numbers correctly. So putting this into a calculator and finding our answer will get us a final value for our entropy change of 181 joules per Kelvin per mole. So as this is a change in entropy, it's still just going to be using the standard unit for entropy, which, as the table shows us here, is joules per Kelvin per mole, and also, as is shown on our answer line, is joules per Kelvin per mole. So we would write that our 181 here. As we have the units on our answer line, we aren't going to get any marks for our unit. Our first mark is going to be for this line in the equation here, substituting in those numbers to our equation correctly, and this line here with our final answer. Calculate a value for the Gibbs free energy change, delta G, in kilojoules per mole for the reaction between ammonia and oxygen at 600 degrees Celsius. If you are unable to obtain an answer to question 3.1, you should assume that the entropy change is 211 joules per Kelvin per mole. This is not the correct answer, and this question is worth 2 marks. So the question is worth 2 marks, which means we are going to get 1 mark for our final value. So that's the value of the Gibbs free energy change, and there's going to be 1 mark for the working. So in order to solve this question, the first thing we're going to need to understand is the equation for how we're actually going to calculate the Gibbs free energy change, our delta G. So the equation is delta G is equal to delta H, that's the enthalpy change, minus T, that's the temperature, delta multiplied by delta S, that's the entropy change. So we have 3 quantities that we're going to need in order to be able to calculate delta G. That's our Gibbs free energy change. So we just need to work out the 3 values of these, then we can substitute them into the equation and calculate the Gibbs free energy change. So first of all, the enthalpy change, delta H, is the simplest of these 3, as we've been given it immediately at the beginning of this question, which told us that the value was minus 905 kilojoules per mole. So we can see that this is the value we can use, as it is in the same units as our answer, so we aren't going to need to do any changes to that to change the units it's measured in. Next up in our equation after our enthalpy change is temperature. So temperature, the question tells us here, just here, is 600 degrees Celsius. However, looking at the units for our entropy change, we can see that in this question, temperature is not measured in degrees Celsius. And in fact, this is the case for whenever we are calculating the Gibbs free energy change. Temperature is not being measured in degrees Celsius. Instead, it is being measured in Kelvin. So we need to convert from 600 degrees Celsius to the equivalent value in Kelvin. The way we convert from degrees Celsius to Kelvin is simply to add 273. So we've got 600 plus 273 Kelvin, which is 873 Kelvin. So that's temperature calculated. We now need to work out the value of the entropy change, which is what we calculated in 3.1. So delta S was equal to 181 joules per Kelvin per mole. However, if we look at the other units present in this question, and most importantly the unit our answer is being measured in, we are not actually using joules as our unit of energy. Instead, kilojoules are used. So we need to convert this value, our entropy change, whether we have used our value or the value given to us by the question if we were not able to obtain an answer in the previous one. We need to convert this to kilojoules per Kelvin per mole. And the way we do this is just the same as converting between joules and kilojoules. We simply divide by 1,000. So this is going to be 0.181 kilojoules per Kelvin per mole. So now everything is all in consistent units. Any temperatures are in Kelvin, any energies are in kilojoules. We can substitute these numbers into our equation, which is going to get us delta G is equal to minus 905 minus 873 multiplied by 0.181. And this is going to get us, if we put into the calculator, a value of minus 1063 kilojoules per mole, which is what we can write here in our final answer, minus 1063. That would be 1 mark, and then the key bit of working to get the working mark would be the equation once we've substituted in the correct values. One thing to note with this question is that you are still able to get 2 marks if you calculated the entropy change incorrectly in the previous question, or if you use the value they have given to you, as you will not be penalized multiple times for a mistake in the previous part of a question. The reaction between ammonia and oxygen was carried out at a higher temperature. Explain how this change affects the value of delta G for the reaction. This question is worth 2 marks. So we will get 1 mark for explaining just stating the effect on the Gibbs free energy change, and the other mark for explaining why that occurs. The first thing we need to do to be able to work out why the value of delta G is changing and how it's changing is actually look at the equation for the Gibbs free energy change. So that gives this equation is that delta G is equal to delta H minus T delta S. And looking at this equation, we'll find as the effect of an increase in temperature on the effect of the Gibbs free energy change. So this increase in temperature here makes this section of the equation, this T delta S, more positive, as the delta S, our change in entropy for this reaction, is positive. What that does is that as we are then subtracting that, the value of the equation overall, and therefore our Gibbs free energy change, is going to decrease, as we are now subtracting a larger number, a more positive number, from our enthalpy change. What this means is that our delta G, our Gibbs free energy change, becomes more negative. So that means it reduces in size from a scalar perspective, but we want to refer to it as more negative, as it's just more correct when we're talking about the Gibbs free energy change. So delta G becomes more negative. We then want to actually explain why, because this here, delta G becomes more negative, gets us 1 mark, but we need to get that 2nd mark. And this is about the mathematical reasoning we've just gone through. As that temperature increases, the value as a whole decreases, and the reason for that is that the delta S, this entropy change, is positive. If this was negative, then the increase in temperature would actually cause the Gibbs free energy change to become more positive, as we'd end up adding a larger number to this side, as the negative from the entropy change would essentially cancel out with the negative in the equation. So this occurs as delta S is positive for this reaction. So for other reactions, this may not be the same. It is the effect of temperature on the reaction in terms of the temperature's effect on the Gibbs re-energy change is down to the entropy change, and whether the entropy change of the reaction is positive or negative. Platinum acts as a heterogeneous catalyst in the reaction between ammonia and oxygen. It provides an alternative reaction route with a lower activation energy. Describe the stages of this alternative route. This question is worth 3 marks, which means we can expect to see 3 main stages in this alternative route that we want to describe in order to gain those marks. So, the first stage in our alternative route is going to be what allows the platinum to actually act as a catalyst on those reactants, the ammonia and the oxygen. It does this by the reactants are adsorbed, so that means to be like adhered to the surface of, not like taken within, like with absorb with a B. This is adsorbed, like adhere. So the reactants are adsorbed to the platinum catalyst. So by doing this, this allows the platinum to actually act on those reactants, as it's a heterogeneous catalyst, which means it is in a different state. This is going to be a solid platinum catalyst, so it does need to actually be in contact with the reactant gases, the ammonia and the oxygen, in order to act on them. Once it's acted on them, though, we begin to see some reactions between the platinum catalyst and these reactants. And these reactions are obviously going to be reversible, as it is a catalyst, so it's going to be reformed at the end. But the purpose of these reactions is to weaken the bonds in the reactants. So it weakens those nitrogen-hydrogen bonds in the ammonia and the double oxygen-oxygen bonds in the oxygen molecules. And the reason it does this is this frees up those atoms in those reactants to form new bonds and form the products. So this allows the products to form. So this is what catalyzes the reaction. By providing other reactions, giving it this alternative route, it weakens the bonds in the reactant, so less energy is required to break those and start forming the products. However, now the reaction has occurred, and we have the products, but they are still currently attached to that platinum catalyst. So the final step in this alternative route is that the products are released from that catalyst. So this is a process known as desorption, like that. It is the opposite of adsorption. So those 3 steps are going to be our 3 marks. First of all, for saying the reactants are adsorbed to the platinum, they're adhered to the surface of it. Secondly, it's for saying how the catalyst then provides that alternative reaction route, so it's weakening the bonds, which means less energy is needed to start forming those products. And finally, it's about saying that the products are released from the catalyst in desorption. The term desorption is not necessary to score the mark. We just need to get across that idea that once the products have been formed, they are released from the catalyst. They're no longer just stuck to the catalyst. Deduce the change in oxidation state of nitrogen when ammonia is oxidized to nitrogen monoxide. This question is worth 1 mark, so we can expect to only get the 1 mark for stating the change and no marks for anything else. So in order to work out the change in the oxidation state, we're going to need to work out the oxidation state in ammonia and the oxidation state in nitrogen monoxide. So we'll start with ammonia. In ammonia, the hydrogen atoms each have an oxidation state of +1. And so what we can expect is a total oxidation state from those hydrogens of +3. Now, ammonia is a neutral compound, which means that we are going to have an overall oxidation state of 0. This means that this nitrogen atom has to counteract the oxidation states of all of these hydrogen atoms. So if we have +3 total from that, nitrogen is going to have a -3 oxidation state. A similar process can be used for nitrogen monoxide. In nitrogen monoxide, our oxygen is going to have a -2 oxidation state. That's our normal oxidation state for oxygen in compounds. Nitrogen oxide is also a neutral compound, which means that, again, our overall oxidation state is going to be 0. Our nitrogen atom here then is going to have to counteract all of this -2 oxidation state from our oxygen. That means that our nitrogen is going to have a +2 oxidation state. So we've now worked out the oxidation states in both ammonia and nitrogen monoxide. So we can say that we have changed from a -3 oxidation state to a +2 oxidation state. We could also say that the change in oxidation state is +5. So we could say the change oxidation state as what it was to what it is now, or just an absolute change, so +5. We only have to write one of these, so -3 to +2, or +5, but we don't need to put both. It's only the one that we'll need. When ammonia reacts with oxygen, nitrous oxide, N2O, can be produced instead of nitrogen monoxide, NO. Give an equation for this reaction. This is worth 1 mark, which means we're going to get that mark for just writing the balanced equation, and as it's only 1 mark, we're unlikely to need to worry about state symbols, as it hasn't specifically mentioned it, and we don't have any information about the state nitrous oxide is going to be in, although we could deduce from the previous equation and background chemical knowledge that nitrous oxide will be produced as a gas, but with the 1 mark and no mention of state symbols, this is likely unnecessary. Now, the equation which produces NO, we need to look at in order to kind of get a base for what our equation that produces nitrous oxide is going to look like. So that equation is 4 moles of ammonia plus 5 moles of oxygen produces 4 moles of nitrogen monoxide plus 6 moles of water. And the key to take away from this equation is that our products are our nitrogen oxide and our water. So what we can expect to see in our equation for this new reaction is ammonia plus oxygen gives us nitrous oxide plus water. So we can start finding our equation by writing that onto our answer line. Ammonia plus oxygen is going to give us nitrous oxide, so that's N2O, plus water. And now we need to go about balancing this equation. So we need to look at the number of each atom on either side of our equation and determine what we need to edit and how many moles we're going to need of each of our reactants and products in order to produce a balanced equation. So we're going to start by looking at our nitrogen atoms as they are the first in our reaction. So we have 1 nitrogen atom on this side, and looking at the other side we can see that we have 2 from our nitrous oxide. So we're going to jot down a 2 as a note that we're going to need 2 of that. If we have 2 moles of our ammonia, we are going to have 6 atoms of hydrogen on this side. So we need to look at how we could use that in order to look at the other side of the equation in order to balance that out as well. So looking over here, we can see that we only have the 2 atoms of hydrogen currently, but we could fix that by placing a 3 in front of our water. So that would give us 6 atoms of hydrogen total, because we would have 3 times 2. However, that would also give us 1, 2, 3, 4 atoms of oxygen on this side, whereas we only have the 2 on this side. So we would have to adjust the number of oxygen molecules we have, the number of moles of oxygen, and put a 2 here as well. Now that isn't going to affect any other atoms because we are only increasing the number of oxygen atoms. So we can quickly check each atom to see if we have the same number of each on either side,
And if this works, then we can write our numbers in properly. So we have 2 moles of nitrogen atoms on this side, 2 on this side, 2 times 3 atoms of hydrogen here, so that's going to be 6, and then over here we have 3 times 2, so that's also going to be 6. We then have 2 by 2, so that's 4 atoms of oxygen, and then 1, and then 3 by 1, so that's 1 plus 3, which is 4 atoms of oxygen on this side. So overall, these numbers all work out, so we can write those in properly as 2 moles of ammonia plus 2 moles of oxygen produce 1 mole of nitrous oxide and 3 moles of water.
This question is about S-block metals. Give the full electron configuration for the calcium ion Ca2+. This question is worth 1 mark, which means we only need to give that configuration. There doesn't need to be any explanation or justification about it. Now, the periodic table shows us that the atomic number for a calcium atom is 20. That means it's going to have 20 protons and therefore 20 electrons in the atom. This would mean that its atomic electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, as the 4s orbital is filled before the 3d orbital. And if we go through and add these electrons, we will find this totals 20, which is the number of electrons in a calcium atom. However, this question doesn't ask about a calcium atom, it asks about a calcium ion, 2+ ion to be specific. So we need to look at the atomic electron configuration and see how this atom is going to lose its electrons in order to form a 2+ ion. And in this case, we need to understand that the electrons are going to be lost from the 4s orbital, as that is the highest energy orbital there. So the ionic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and then it will stop as the 2 electrons in the 4s orbital have been lost from the atom, which is what has ionized it to form the 2+ ion. Explain why the second ionization energy of calcium is lower than the second ionization energy of potassium. This question is worth 2 marks, which means we are going to need to make 2 distinct points to gain both of these marks. So the ionization energy, and whether that's first or second ionization energy of an element, is going to be based on its electron structure. The value of that ionization energy is going to come down to the electron structure of it, and also the nuclear charge of these elements. And in this situation in particular, we are looking at the second ionization energy, which means that instead of going from Ca and K, just our atoms, we are instead going from Ca plus and K plus, our +1 ions, as the first ionization has already occurred. We are looking at second ionization energy. So we need to consider what the electron structures of each of these elements are going to be like now that they've been ionized, as they will have both lost an electron from their 4s orbital in this case. And that gives us a clue as to what the first reason that the calcium's second ionization energy is lower, and that is that in our calcium ion, that's our Ca+, the valence electron, that's our outermost electron, is in a higher energy orbital. And this is because our calcium, when it's an atom, has 2 electrons in its 4s orbital, whereas in our potassium, when it's an atom, it only has 1 electron, which means once it's been ionized once, the calcium ion still has 1 electron in its 4s orbital, whereas the potassium ion no longer has any electrons in its 4s orbital. This means that when it comes to our second ionization, when it's calcium, we are removing another electron from the 4s orbital, but in potassium, we're starting to remove from the 3p orbital. This means that our potassium's valence electron is at a lower energy than we are in calcium, so we're going to need more energy to make up for that difference when we're trying to remove that electron. So the first point is about the position of the valence electron. So we've talked about the fact that it's in a higher energy orbital, but you could also talk about distance from the nucleus, as the 4s orbital is actually a further physical distance from the nucleus than the 3p orbital. But both of these would be the same mark. So if you were to write both of those, you would only get 1 mark. Now the second mark is less about the position of the valence electron and more about the structure of and how the rest of the electrons in the ions are going to affect the ionization energy. And specifically what we'll talk about is shielding. So in our calcium ion, there is more electron shielding on the valence electron. And this is because, again, it's in the 4s orbital. So that means in calcium, that valence electron is being shielded by the 3p orbital. Whereas in potassium, because our valence electron is within that 3p orbital, that all the other electrons in that orbital aren't shielding it from the nucleus at all. And as a result, there's less sort of repulsive forces on that valence electron in potassium as compared to calcium. So it's easier to remove the electron in calcium. Therefore, we're going to have a lower second ionization energy because we have more electrons sort of shielding it from the nucleus. So it's experiencing a lower effective force from the nucleus. So that would be our second mark, mentioning electron shielding. So the first is position of the electron, second is electron shielding, what the rest of the electron structure is doing to affect the ionization energy. Identify the S block metal that has the highest first ionization energy. This question is worth 1 mark. So it's worth 1 mark, which means all we need to do is identify this metal. We don't have to give any justification as to why it is that metal. In order to work this out, we need to think about the factors which affect ionization energy. And the most important one to start with that will help us narrow down which S block metal will have the highest first ionization energy is going to be electron shielding. So electron shielding is where the other electrons in an atom that are between the outermost electron and the nucleus repel that outermost electron, meaning that it feels less of an attractive force towards the nucleus overall, less of a lower effective force. This means that the fewer electrons between the nucleus and the valence electron, the higher the first ionization energy will be, as the effective force it's experiencing from the nucleus will be as high as possible. This narrows our S block metals down to just the 2 that are at the top of each of the groups. As we go down the groups, the number of electrons in terms of each filled main energy level increases. So that narrows it down to lithium and beryllium. From here, we need to consider if there are any other factors between that will affect that first ionization energy. And the key one to consider is going to be nuclear charge. So once again, this is about the attraction that the valence electron feels to the nucleus. And that attraction is going to be stronger the greater the charges that are being attracted. Now, the charge on the electron is consistent, so that's not going to change. However, the number of protons in the nucleus is not consistent. That does change between the different elements. So, in the difference between these two, beryllium has 1 more proton in its nucleus than lithium does, which means it's going to exert a greater attractive force on that valence electron. So it's going to require more energy to ionize that beryllium and pull the valence electron away from it. So beryllium has the highest first ionization energy of all of the S block metals. And we could write beryllium, or we could write the symbol. Either would be acceptable to get the mark. Give the formula of the hydroxide of the element in group 2 from magnesium to barium that is least soluble in water. This question is worth 1 mark, which means we just need to give the formula. We don't have to justify or explain our answer at all. Now, when it comes to the hydroxides of group 2, the solubilities in water increase down the group. This means that as the element at the top of the group, or the top of the section of the group we're looking at, that is, magnesium hydroxide is going to be the least soluble. However, we aren't just looking for the name of this hydroxide, we do need to actually give the formula for it. So we need to look at the ions involved in order to be able to find that formula. So as magnesium is a group 2 element, it's going to form a 2 plus ion, whereas the hydroxide ions are simply 1 minus. So looking at that, we can see that we're going to need 2 hydroxide ions for our magnesium ion. So our formula is going to be 1 magnesium and then 2 hydroxide ions. OH, so R, just Mg and then OH, and then all of that OH too. A student added 6 centimeters cubed of 0.25 moles per decimeter cubed barium chloride solution to 8 centimeters cubed of 0.15 moles per decimeter cubed sodium sulfate solution. The student filtered off the precipitate and collected the filtrate. Give an ionic equation for the formation of the precipitate, show by calculation which reagent is in excess, and calculate the total volume of the other reagent which should be used by the student so that the filtrate contains only one solute. This question is worth 3 marks. Now, our first mark is going to be for giving the ionic equation. We're only going to get the 1 mark for it, which means we are providing no explanation or justification for it, we just need to write that equation. Now, we should, before we can write the ionic equation, we should identify what's occurring in this reaction. So we have our barium chloride, that's BaCl2, and our sodium sulfate, that's Na2SO4, reacting to form barium sulfate, that's BaSO4, and 2 moles of sodium chloride, that's NaCl. So we can see from this that we have a displacement reaction which ends up forming barium sulfate and sodium chloride. Now, from our knowledge of the solubilities of group 2 hydroxides and sulfates, we know that the solubilities of the group 2 sulfates decrease down the group. And now, as barium is right at the bottom of group 2, we will find that barium sulfate is very insoluble. So we can say that this precipitate is going to be barium sulfate. So we can use this to start writing our ionic equation, as the formation of this precipitate is going to be the aqueous ions coming together to form this solid precipitate. So our aqueous ions in this instance are Ba2 plus aqueous. So this is our positive barium ion. Then we have our sulfate ion, so that's SO4 2 minus. This is also aqueous at the moment. So that's our sulfate ion, and these form barium sulfate, which is a solid, as it is our precipitate. So now that we have done this is our first mark, we can move on to calculating the reagent in excess. Now, the way we need to do this is by using the numbers provided at the beginning of the question, which allow us to calculate the number of moles of each of our reagents. As we can see via the reaction equation that our reagents are going to react in a 1-to-1 ratio. So all we need to do is calculate the number of moles and see which has more moles. So in order to do this, we are going to use moles is equal to concentration times volume. So to start with our moles of barium chloride, so moles of barium chloride, that's our BaCl2, we need to do 0.25 multiplied by, and before we use our value for volume, we need to convert it from centimeters cubed to decimeters cubed, as that's what's being used in our unit for concentration. So the way we're going to do that is by dividing by 1000. So we're going to multiply it by 6 over 1000, which will get us a value of 1.5 times 10 to the minus 3 moles. Now that we have calculated our value for barium chloride, we need to calculate the value for our sodium sulfate. So we are now going to calculate moles of sodium sulfate, Na2SO4. So in order to do that, again, we're going to be using concentration times volume. So this time our concentration is 0.15, and again, our volume is measured in centimeters cubed, so we need to divide by 1000. So we're going to have 8 over 1000, and that is going to get us a value of 1.2 times 10 to the minus 3 moles. So now that we've done this, we can compare our two values, and we can see that 1.5 times 10 to the minus 3 is higher than 1.2 times 10 to the minus 3. So therefore, the reagent in excess is our barium chloride. Now, this is only worth 1 mark. However, we do need to, as the question asks us to show this, we can't just write barium chloride. We need to show this working in order to get that mark. So all of this, both the working and then stating barium chloride, is required for that mark. Now that we've done that, we can look at the final section of the question, which asks us to find the total volume of the other reagent, so that's the sodium sulfate, we need to add in order to ensure there is no other no other solute present in the filtrate. So what we need to do is see how much more of this reagent, this sodium sulfate, we need to add in order to ensure a complete reaction. And the way we are going to do that is start by looking at the difference in moles. So there were 1.5 times 10 to the minus 3 moles of barium chloride, but only 1.2 times 10 to the minus 3 moles of sodium sulfate. So we are going to need to find the difference in moles, which is going to be by doing 1.5 times 10 to the minus 3 minus 1.2 times 10 to the minus 3. This is going to get us 0.3 times 10 to the minus 3 moles. So now we need to use this to work out how much of what volume of our sodium sulfate we're going to need to add in order to make up 0.3 times 10 to the minus 3 moles. Now, the way we're going to do that is by rearranging our equation, which links moles, concentration, and volume. So what we will see is that volume is equal to moles divided by concentration. So what we need to do in order to find our volume is to do 0.3 times 10 to the minus 3 divided by 0.15, which is going to get us a volume of 0.01 decimeters cubed, which is the same as 10 centimeters cubed. So we need that 10 centimeters cubed is what we need for our final mark. So that's the third mark of the question, as that's the volume we need to add to ensure a complete reaction. A sample of strontium has a relative atomic mass of 87.7 and consists of 3 isotopes: strontium-86, strontium-87, and strontium-88. In the sample, the ratio of abundances of the isotope strontium-86 to strontium-87 is 1 to 1. State why the isotopes of strontium have identical chemical properties, and calculate the percentage abundance of the strontium-88 isotope in the sample. This question is worth 4 marks. So, to begin with, for stating why the isotopes of strontium have identical chemical properties, this is only going to be worth 1 of the 4 marks, as it is only asking us to state the reason. We don't require any explanation of that reason or justifying it. We only need to state it, and that's just the 1 mark. So the reason isotopes of strontium all have the same chemical properties is the same as the reasons that isotopes of any element all have the same chemical properties, and that is that isotopes only differ in the number of neutrons. They all have the same electron structure or electron configuration, and it's this electron configuration that determines the chemical properties of an atom. So as all the isotopes of strontium have the same electron configuration, they all have the same chemical properties. Now that we have stated why the isotopes all have identical chemical properties, we can move on to calculating the percentage abundance. Now the question has only given us 2 bits of information. First of all, that the ratio of abundances between the strontium-86 and strontium-87 isotopes, that's our strontium-86 and our strontium-87, is 1 to 1. The second piece of information that it's given us is that the relative atomic mass of strontium is 87.7. Now, relative atomic mass is an average. It's the average mass of all the atoms of an element. But from these 2 pieces of information, we can calculate the percentage abundance of the strontium-88 isotope. Now, the way we need to do this is by using the fact that the relative atomic mass is an average, and we're going to be forming an equation almost like the calculation of a mean. In order to do this, we're going to use the term X to refer to the percentage abundance of both the strontium-86 and the strontium-87 isotopes, as they are the same, so we can use just the one. So let's start producing that equation. We're going to start with the mass of the strontium-86 isotope, multiplied by its abundance, X. We're going to add the mass of the strontium-87 isotope, 87, multiplied by its abundance, X. And then we need to add the mass of the strontium-88 isotope, so 88, multiplied by its percentage abundance. Now, as there are only the 3 isotopes, and the total percentage abundance is 100, the percentage abundance of 88 is going to be 100 minus 2x, as that will find us what is left of the abundance after these 2 isotopes have been taken out of that. Then we need to, just like when we're finding the mean, we need to divide by the total number here. So in this case, the total percentage abundance is 100, as that's the total of a percentage. And then we need to say what this is equal to. So this finds us the average mass, which is our relative atomic mass. So this is going to be equal to 87.7. Now that we have got to this point, we can start finding our percentage abundance by rearranging this equation. So the first thing we're going to do is move this 100 over to the right-hand side. It's currently a divide by 100, so it's going to become a multiply by 100. So we're going to have 86x plus 87x plus 88 by 100 minus 2x is equal to 87.7 times 100, which is 8,770. The next thing we're going to do is expand these brackets here. So we're going to multiply each term in the bracket by that 88. So these terms in the front are going to stay the same. It's still going to be 86x plus 87x. But then we are going to have 8,800 minus 176x. And that's still equal to 8,770. Then, moving on, the next thing we want to do is collect all of our x terms. So we're going to add up these 3 terms. So 86x, 87x, and minus 176x. 86 plus 87 is going to get us 173. So minusing 176 off of that will get us minus 3x plus 8,800 still, and then that's still equal to 8,770. Now we're going to rearrange this a bit more. So this minus 3x is going to come over to the right, becoming a plus 3x. This 8,770 is going to go over to the left, becoming a minus 8,770. So on this left-hand side, we have 8,800 minus 8,770, so that's going to get us 30. And on the right-hand side, we're just going to have 3x. Then we can divide through by 3, giving us our value of x, finding that x, which is the percentage abundance of the other 2 isotopes, not our strontium-88, is 10. All we need to do now is use what we worked out earlier, and that the abundance is equal to 100 minus 2x, and then we can substitute in the 10 we've just worked out to get the abundance is 100 minus 2 lots of 10, which is 100 minus 20, which gets us our percentage abundance of the 88 strontium isotope as 80%. So this question in total was worth 4 marks. One of those marks was for stating the reason behind the chemical properties of the isotopes. The remaining 3 marks are all for this calculation. One of those is this final answer of the 80%, but the remaining 2 are method marks. The first being for this calculation here, which ties together the percentage abundances and the relative atomic mass, and the other is for the calculation of this x equals 10, with the for the calculation being that final 80%. And that's the 4 marks for this question. A time of flight, TOF, mass spectrum was obtained for a sample of barium that contained the isotopes barium-136, barium-137, and barium-138. The sample of barium was ionized by electron impact. Identify the ion with the longest time of flight. This question is 1 mark, which means all we need to do is give the formula of the ion. We don't need to justify or explain why it's that one at all. Now, when it comes to time of flight mass spectrums, they are obtained when by accelerating all of the ions to the same kinetic energy, and then they all travel through the same length flight tube. This means that our highest mass ions are going to travel the slowest and take the most time, as kinetic energy, as they're all the same kinetic energy, a higher mass means a lower velocity. Therefore, it's going to be barium-138 that will take the longest, have the longest time of flight. However, we can't just write 138Ba like this, as we need to remember that they have been ionized, as it says here, by electron impact. That means that we are going to have +1 ions, so it's going to be 138Ba plus, and that is the form of the ion we need for our 1 mark. A 137 mass barium ion travels through the flight tube of a time of flight mass spectrometer with a kinetic energy of 3.65 times 10 to the minus 16 joules. This ion takes 2.71 times 10 to the minus 5 seconds to reach the detector. The question also gives us the equation for kinetic energy, which is half mv squared, where m is the mass in kilograms. That's important to note, as the majority of equations in chemistry use mass in grams, not kilograms. And v is the speed measured in meters per second. It also gives us the value of the Avogadro constant, L, which is 6.022 times 10 to the 23 moles to the minus 1. We need to calculate the length of the flight tube in meters, giving our answer to the appropriate number of significant figures. This question is worth 5 marks. Only one of these marks is going to be for the value of our final answer. We can expect the remaining 4 to come from the working in this question. Now, in order to calculate the length of the flight tube, we are going to need to know the speed of our ion. And in order to work that out, looking at our kinetic energy equation, we can see that we're going to need to know the mass of our ion. And we need to know the mass of one ion specifically. It does give us a mass here with 137, but that is the mass in grams of 1 mole of these ions. Whereas we need to calculate the mass of a single ion. And the way we're going to do that is by taking the mass of 1 mole and dividing by the number of ions in that mole, which is the value of the Avogadro constant. However, we need something that's important. As I noted earlier, we need to use this mass in kilograms, not grams. So, rather than using 137 divided by 6.022 times 10 to the 23, we are going to divide it by 1,000 to convert it to the number of kilograms that that mole weighs, which is going to be 0.137 over 6.022 times 10 to the 23. And this will get us a value of 2.275 times 10 to the minus 25 kilograms for the mass of one of these 137 barium plus ions. Now that we have this value here, we can start finding the value of our velocity. And to begin with, we can see our kinetic energy equation, which is Ke is equal to half mv squared. Now this uses v squared, so to begin with we're just going to rearrange to find the value of v squared. So v squared is equal to 2 times Ke, as we've moved this half over, and it's currently a divide by 2, it's now multiplied by 2. We're going to then move the mass over as well, so that's going to become a divide by mass, so we're going to have 2 Ke over our mass. This gives us an equation that we can substitute our numbers into, so we're going to have 2 times 3.65 times 10 to the minus 16 divided by 2.275 times 10 to the minus 25. And calculating that will get us a value of 3.2088 times 10 to the 9. Now that we have worked this out, we can calculate v by finding the square root of this value. So v is equal to the square root of 3.2088 times 10 to the 9, which gives us the value for our speed of 5.6696 times 10 to the 4. Now that we have our value of velocity, we can use that to find the length of the flight tube, as the distance travelled is equal to the speed multiplied by the time. So substituting in our numbers, we are going to have 5.6696 times 10 to the 4 meters per second, that's our speed, multiplied by our time of flight, which was 2.71 times 10 to the minus 5, which is going to get us a value of 1.536 meters. Now we need to give this to an appropriate number of significant figures. So if we look back at our question, we will see that the majority of our quantities that we were given in the question were given, not counting our Avogadro constant, as that's a constant rather than a value given to us specifically by the question, are to 3 significant figures. So we are going to have to give this value to 3 significant figures. So we'll go along by 3. So our first significant figure is the 1, then it's the 5, then it's the 3. So we're going to round based off the 3. Looking at the next digit, we can see it's a 6, so we'll round up. So this is equal to 1.54 meters. Now, that 1.54 meters, to our appropriate number of significant figures is only one of the marks. The 4 marks that are for the method. The first comes for calculating the mass of one ion in kilograms. The second comes from rearranging our kinetic energy and calculating the square of our speed. The second then comes from square rooting that to find, the third comes from square rooting that to find our speed, and the fourth comes from multiplying our speed by time to calculate the distance. Hydrochloric acid is a strong acid and ethanoic acid is a weak acid. State the meaning of the term strong acid. This question is worth 1 mark, which means we don't need any justification or explanation for that definition. It's just one key point in our definition, and that will be that 1 mark. So the strength of an acid refers to the degree in which it dissociates in solution, rather than anything like how corrosive it is or its pH. So to be specific, a strong acid is an acid which completely dissociates in solution. This is in contrast to a weak acid, which is only going to partly dissociate. So the acid in solution dissociates into ions, so we could also, instead of saying dissociates, the term ionizes could also be used to gain that mark. In an experiment, 10.35 centimeters cubed of 0.1 moles per decimeter cubed hydrochloric acid are added to 25 centimeters cubed of 0.15 moles per decimeter cubed barium hydroxide solution. And we need to calculate the pH of the solution that forms at 30 degrees Celsius. We've been given the ionization constant of water at this temperature, so that's at 30 degrees Celsius, which is equal to 1.47 times 10 to the minus 14 moles squared per decimeters to the minus 6. And we need to give our answer to 2 decimal places. We would need to do this regardless, as we're calculating a pH, and pH should always be measured to 2 decimal places. The question is worth 6 marks, so we are going to have 5 marks for our working, and our final 6 mark for our value of the pH. So we need to start this question off by calculating the values of moles we have for each reagent. As we can see, we have an acid and a base, so they are going to react, so we need to know how many moles of each we are going to have left after this reaction, or which one is in excess, so how many moles of that will be left over after that reaction. So the way we're going to calculate moles is by using moles is equal to concentration times volume. So to work this out with hydrochloric acid, we are going to do 0.1 multiplied by, and we need to multiply, so this is our concentration, but we need to multiply by the volume. That's not just going to be 10.35, as it's in centimeters cubed here, and we need decimeters cubed for our unit. So we're going to divide by 1,000 to convert centimeters cubed to decimeters cubed. So we're going to get 0.01035, which is going to get us a value for the moles of hydrochloric acid at 1.035 times 10 to the minus 3 moles. Then we're going to do the same for our barium hydroxide. So for our barium hydroxide moles, it's going to be the same equation, but with the values for barium hydroxide, so it's going to be 0.15 multiplied by, and again we need to convert from centimeters cubed to decimeters cubed, so dividing by 1,000 once again, we're going to get 0.025, which is going to get us a value of 3.75 times 10 to the minus 3 moles of barium hydroxide. However, we aren't quite done working out the moles we need for the reaction yet. And that's because hydrochloric acid is a monoprotic acid, so we're only going to get one hydrogen ion out of this. So these moles here are equivalent to the moles of our hydrogen ions. However, barium hydroxide does not produce only one hydroxide ion, it produces 2. So we actually need to multiply our 3.75 times 10 to the minus 3 by 2 in order to get the moles of our hydroxide ions. And that is going to get us 7.5 times 10 to the minus 3 moles. And we need to do this as in an acid-base reaction like this, it's the hydroxide ions which are reacting with the hydrogen ions. So yeah, we need to know the moles of hydroxide ions more than just the moles of the barium hydroxide, as it's the hydroxide ions which are actually the active part of this reaction with our hydrogen ions. Now that we've done that, we can compare our two values. As the hydrogen ions and the hydroxide ions will react in a 1-to-1 ratio, we can see that there are less moles of hydrogen ions. So there's going to be 1.035 times 10 to the minus 3 moles that are reacting, which is going to leave the remainder of the hydroxide ion. So the way we're going to find that is by doing 7.5 times 10 to the minus 3 minus 1.035 times 10 to the minus 3, which is going to leave us a total of 6.465 times 10 to the minus 3 moles. So now that we have this value, we have the moles of hydroxide ions left after the reaction has taken place. So using this, we now need to start calculating the concentration of our hydroxide ions. So that's our square brackets OH minus here. Now, rearranging this equation, we will see that concentration is equal to moles divided by volume. So we're going to have 6.465 times 10 to the minus 3 divided by the total volume of the solution. So because we had 10.35 centimeters cubed of hydrochloric acid and 25 centimeters cubed of barium hydroxide, so in total we're going to have 35.35 centimeters cubed. However, we need that in decimeters cubed, so we're then going to divide that by 1000. So it's going to be 0.03535 decimeters cubed. And that will get us a value for our concentration of 0.182885 moles per decimeter cubed. Now we've got our concentration, we can start to work out pH. However, pH is not calculated from the concentration of hydroxide ions. It's calculated from the concentration of hydrogen ions. So we need to find a way to convert this concentration to our hydrogen ion concentration. And the way these are linked is by the ionization of water, this Kw. Now, Kw is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. So rearranging this, we will find that the hydrogen ion concentration is equal to the ionization constant of water divided by the hydroxide ion concentration. So substituting in our numbers, what we will find is that we have 1.47 times 10 to the minus 14 from our water ionization constant over 0.182885 moles per decimeter cubed. This is going to give us a value for our hydrogen ion concentration at 8.0378 times 10 to the minus 14. We can now use this to calculate our pH, as pH is equal to minus log 10 of our hydrogen ion concentration. So substituting in our value of 8.0378 times 10 to the minus 14 is going to get us a value for pH of 13.09 to 2 decimal places. That's what we need to. That's what the question the request is we state the answer to. So that answer there is our 6th mark, but the remaining 5 will come from the working. So the first of these working marks would have been here for calculating the moles of our reagents. The second comes from calculating the moles of our hydroxide ions. The third then comes from calculating the moles remaining after reaction. And the fourth comes from calculating the concentration of our hydroxide ions, with the fifth then coming from finding the concentration of the hydrogen ions using our ionization of water to find that. So we have 1 mark for our final answer and 5 for our working. The pH of water at 30 degrees Celsius is 6.92. Give the reason why water is neutral at this temperature. This question is worth 1 mark, so we don't need to explain why that's the case. We just need to state the reason, no justification needed. So the key to why water remains neutral at this temperature of 30 degrees Celsius, and indeed at all temperatures, lies in how it ionizes. And to do that, we can look at this equation. Our molecule of H2O ionizes or dissociates to form a hydrogen ion and a hydroxide ion. So looking at this, we can see that every ionization of water, every time a molecule of water dissociates, it produces a hydrogen ion and a hydroxide ion. And the key to water being neutral lies in this. No matter what happens with water, the concentration of hydrogen ions is always equal to the concentration of our hydroxide ions, which therefore means that it's just as acidic as it is alkaline, so therefore it is always neutral. The reason the pH is different from our standard neutral pH of 7 is due to the temperature, as pH is exclusively calculated from the hydrogen ion concentration, and at this temperature we have a greater concentration of hydrogen ions because of the shift in this equilibrium. So while there are more hydrogen ions, there are also more hydroxide ions, so it's still neutral. It just so happens that the neutral pH is different at this temperature. Identify the oxide that could react with water to form a solution with pH equals 2. Tick one box. This question is worth 1 mark. All we need to do is just tick the correct box. So, with this question, it comes down to recognizing and understanding the reactions of the general reactions of oxides with water. Now, these first two oxides are both metal oxides, and in general terms, a metal oxide plus water is going to lead to a basic solution. It's going to form a base, so these will produce hydroxides, which, as it is a basic solution, it is going to not have a pH of 2, it's going to have a pH above 7. Now, silicon dioxide here doesn't cleanly fall into the metal and non-metal categories, as it's a metalloid. However, silicon dioxide is fairly unreactive with water. It's the main constituent in sand. It doesn't really react with water, which leaves just sulfur dioxide. Now, non-metal oxides plus water react to form acidic solutions. So in this case, we are going to end up with a solution of sulfuric acid, which means that out of these four, the only one oxide that would react with water to form a solution with pH of 2, so an acidic solution, as it's a pH of less than 7, is our sulfur dioxide, so we would tick that box, and that would get us that 1 mark. Give the expression for the acid dissociation constant, Ka, for ethanoic acid, that's CH3COOH. This question is worth 1 mark, which means we're going to get 1 mark for giving the expression, and with no explanation or anything added to it. So when it comes to the acid dissociation constant, in general terms, for the acid HX, our Ka is equal to the concentration of our hydrogen ions multiplied by the concentration of our negative ions from our acid. So we'll look at what that negative ion will be in ethanoic acid in a minute, over the concentration of the acid. So now, converting that to the specific acid we have here, ethanoic acid, our hydrogen ions are still going to be the same. This is the same for all acids. Next, we have our negative ion. So in the case of ethanoic acid, that's going to be an ethanoate ion. So that's CH3COO minus. And then this is going to be divided by the concentration of the acid. So that is our ethanoic acid, our CH3COOH. And that is the expression for the acid dissociation constant, which would get us our 1 mark. A buffer solution contains 0.025 moles of sodium ethanoate, dissolves in 500 centimeters cubed of 0.07 moles per decimeter cubed ethanoic acid at 25 degrees Celsius. A sample of 5 centimeters cubed of 2 moles per decimeter cubed hydrochloric acid is added to this buffer solution. Calculate the pH of the solution formed. For ethanoic acid, the acid dissociation constant is equal to 1.76 times 10 to the minus 5 moles per decimeter cubed at 25 degrees Celsius. This question is worth 5 marks. Once again, we can expect to only have 1 of these marks for our answer. The remaining 4 will all be for the working. So to begin this question, the first thing we need to do is calculate the moles of all of our reagents. So we've been given volumes and concentrations for both our ethanoic acid and our hydrochloric acid. So we need to use those to calculate moles. So moles is equal to concentration times volume. So for our ethanoic acid, that's going to be our 0.07 multiplied by 500 divided by 1000, which is going to be 0.5, which is going to get us a value for moles of 0.035. We must divide by the 1000 here to convert the centimeters cubed that this volume is measured in into the decimeters cubed that is used for volume in our concentration unit. When we do the moles for our hydrochloric acid, we have to do the same, and we will multiply our concentration of 2 by 5 divided by 1000 to convert it to decimeters cubed, which is going to be 0.005, which will get us a value of 0.01 moles. Now that we have the two values for our moles, we need to calculate the effect the buffer solution has on this. So our hydrochloric acid is a strong acid, so it dissociates completely, which means these 0.01 moles are all, this 0.01 mole is moles of hydrochloric acid are all going to dissociate. And as it's a monoprotic acid, we are going to get 0.01 moles of hydrogen ions produced into this. What this means is that our sodium ethanoate, which is providing 0.025 moles of ethanoate ions, is going to react with this. So our moles of ethanoate, that's CH3COO-, which are going to be left, is equal to 0.025 minus 0.01, as we are going to have 0.01 moles of it reacting to neutralize the hydrogen ions that have been introduced, reacting with them to remove them from the solution. So we are going to end up with 0.015 moles of our ethanoate ions remaining. However, this isn't the only effect of the buffer, as this reaction between the ethanoate ions and the hydrogen ions needs to form something, and what it forms is ethanoic acid. So while we lose 0.01 moles of ethanoate ions, we gain 0.01 moles of ethanoic acid. So our moles of ethanoic acid is equal to the 0.035 we calculated plus 0.01, which is going to get us 0.045 moles of ethanoic acid now. Now that we have done this, we need to start calculating our pH. And pH is based off of our concentration of hydrogen ions, and the way we are going to find that is by using our acid dissociation constant. So for ethanoic acid, the equation for this looks as follows. We have the concentration of our hydrogen ions multiplied by the concentration of our ethanoate ions divided by the concentration of our ethanoic acid. So rearranging this to find the concentration of our hydrogen ions, we will see that we have our acid dissociation constant multiplied by the concentration of our ethanoic acid divided by the concentration of our ethanoate ions. So now we can begin to substitute in the numbers that we've calculated and the question has given us in order to find the hydrogen ion concentration. It's important to note that for our concentrations, though, when we will calculate those in the question, the volume we will use will be the total volume of our solution. So that's the volume that was provided by the ethanoic acid, so that's 0.5 decimeters cubed, and the volume provided by the hydrochloric acid, which is 0.005 decimeters cubed. So our total volume is going to be 0.5 plus 0.005. So the value of our acid dissociation constant is 1.76 times 10 to the minus 5. That is going to be multiplied by our ethanoic acid concentration. So that's 0.045 divided by 0.505. This is moles over volume. And then that is going to be divided by our ethanoate concentration, which is 0.015 divided by 0.505. Now, this is going to give us a value of 5.28 times 10 to the minus 5 moles per decimeter cubed. And now we can use this to find pH, as pH is equal to minus log 10 of our hydrogen ion concentration, which is equal, therefore, to minus log 10 of 5.28 times 10 to the minus 5, which is going to get us a final value for our pH of 4.28. This is measured to 2 decimal places, as all pH should always be measured to 2 decimal places. And that will be our 5th mark for the question,
just the one, just the one for our final answer. The remaining 4 come in the working. So what we will see is our first working mark comes for calculating the number of moles of our ethanoic acid and our hydrochloric acid. Then marks 2 and 3 come from calculating the moles of our ethanoate ions and our ethanoic acid after the reaction. So mark 2 for the ethanoate moles, mark 3 for the ethanoic acid moles. And then mark 4 for the working comes from these lines here, the rearranging of the acid dissociation constant expression to find our value of the hydrogen ions. So 4 marks for working, 1 mark for our final answer for pH, which should be given to 2 decimal places, as pH always should be. A student set up the cell shown in figure 2. Figure 2 shows us that in the left half cell we've got a copper electrode with 0.15 moles per decimeter cubed of copper sulfate solution, and in the right half cell we also have a copper electrode, but this time we have 1 mole per decimeter cubed of copper sulfate solution. The student recorded an initial voltage of 0.16 volts at 25 degrees Celsius. Explain how the salt bridge provides an electrical connection between the two solutions. This is worth 1 mark, so we just need to state this reason with no further justification for it. So looking at our figure 2 here, we can see that when moving between the cells, the one way the ions can do this is via the wires the wire that is connecting the electrodes to the voltmeter. However, when they need another route to move back the other way in order for this to be a complete circuit and to actually get an electrical connection here. And that's what the salt bridge does. The salt bridge, it allows for the movement of our charged particles. And what's important with our electrochemical cells is to make sure to remember that they are ions that are moving through the cell. It's not electrons, like in a lot of traditional circuits. It is ions. So we need to make sure to say ions to get that mark. If you say electrons, you won't get this mark. But this statement here is what we'll get as the mark for explaining what the salt bridge does, as it allows for the movement of ions, not electrons, through it. The standard electrode potential for the copper 2 plus copper electrode, which is represented by this reaction here, where we have a copper 2 plus ion gaining 2 electrons to form solid metallic copper, is 0.34 volts. Calculate the electrode potential of the left-hand electrode in figure 2. This is worth 1 mark, which means all we need to do for that mark is just give our answer. There aren't going to be any working marks here. Now, in this question, our total potential for our cell was 0.16. And the way we would calculate this is by doing the potential of the right-hand electrode subtract the potential of the left-hand electrode. Now, the potential of the right-hand electrode is going to be equal to our standard electrode potential, as it is a standard copper 2 plus copper electrode, as it's under room temperature and pressure, and it has a concentration of 1 mole per decimeter cubed of our copper sulfate solution. This means that our right-hand potential is 0.34, and we would subtract from that the potential of our left-hand electrode. So now we can rearrange this to find our left-hand electrode's potential. So we'd move this over, the potential of the left-hand electrode over to the left, and the 0.16 total potential over to the right, to get the potential of the left-hand electrode is equal to 0.34 subtract 0.16, which is going to get us the value of plus 0.18 volts. So that is all we need to write for our mark. The working doesn't actually get us any mark, it's just our final answer that's worth our 1 mark.
Both electrodes contain a strip of copper metal in a solution of aqueous copper 2+ ions. State why the left-hand electrode does not have an electrode potential of 0.34 volts. This question is worth 1 mark, so we just need to make that statement and we don't need any further justifications. Now, this electrode potential here of 0.34 volts matches the standard electrode potential for the copper 2+ electrode. So we would expect a copper 2+ electrode to have this potential. However, this is the standard electrode potential, which means it's measured under standard conditions. These standard conditions include temperature, pressure, so this is room temperature and pressure, and also concentration. And it's this last one that's important for this question. And the reason for this is the left-hand electrode does not have the standard concentration, which means it's not going to have the standard electrode potential. So this standard concentration is 1 mole per deciliter cubed. So it's 1.0 moles per deciliter cubed. So the fact it doesn't have this standard concentration means it's not going to have the standard electrode potential for its type of electrode. And that statement there is all we need to get the 1 mark. Give the conventional representation of the cell in figure 2. Include all state symbols. This question is worth 1 mark. So we're going to need to give the full conventional representation and the state symbols all correctly in order to gain that mark. Now, in figure 2, both cells contained 2 forms of the copper. There was the solid copper present in the electrodes as a solid, and then there was the 2+ ionic copper, which were present in the solution as aqueous ions. When it comes to the conventional representation of cells, though, going from left to right, we have first of all the most reduced species in the left half cell. We then have a single vertical line which represents a phase boundary. So in this case, it's the boundary between our solid copper and our aqueous copper ions. And then we have, after this single vertical line, we have the most oxidized species in the left-hand half cell. Then we have a double vertical line, which represents the boundary between the 2 half cells. Then we have the most oxidized species in the right-hand half cell. Then another single line representing another phase boundary between the most oxidized species in the right-hand half cell and the most reduced species in the right-hand half cell. So, in the case of this cell, the most reduced species is the solid copper. Then we will have our single line representing a phase boundary. Then the most oxidized species in the left-hand half cell, which is our ionic copper, which is aqueous. Then we have the boundary between the 2 half cells, which is our double vertical line. And then we will have the most oxidized species in the right-hand half cell, which is also the ionic copper. Again, it is still aqueous. Then we will have another single vertical line, which represents a phase boundary, and then the most reduced species in the right-hand half cell, which is the solid copper. So we need all of this representation, including the state symbols, to get this 1 mark. When the voltmeter is replaced by a bulb, the EMF of the cell in figure 2 decreases over time to 0 volts. Suggest how the concentration of copper 2 ions in the left-hand electrode changes when the bulb is alight. Give 1 reason why the EMF of the cell decreases to 0 volts. This question is worth 2 marks, so we can expect to see 1 mark for each part. So as it's just 1 mark for each part, we just need to state each of these rather than giving any amount of justification to those answers. Now, when it comes to the change in concentration of copper-2 ions in the left-hand electrode, we need to consider what the two electrodes are like at the beginning of this cell before it's turned on. To begin with, the right-hand electrode has got a higher concentration of copper-2 ions than the left-hand electrode. And this means that over time, once the cell's connected, we're going to slowly see a net movement of these ions from the higher concentration to the lower concentration. This is diffusion. So what we can expect to see is that the concentration of copper-2 ions in the left-hand electrode increases as the concentrations begin to level out between the two electrodes. And this actually gives us the reason why the EMF decreases to 0 volts. Because over time, as the concentration of copper-2 ions in the left-hand electrode increases, eventually the concentrations of our copper 2 plus ions are going to become equal in both of the half cells. And this means that the EMF is going to become 0 as there's no longer a difference between the half cells. So there is no reason for the electricity to flow anymore. So as the copper-2 ions slowly diffuse and form sort of an equilibrium between the concentrations in the two different electrodes, the concentration in the left-hand electrode is going to increase, and the EMF is eventually going to become 0 as those concentrations are going to become equal. So each of these statements is worth the 1 mark, and together they make up the 2 marks for this question. When anhydrous aluminium chloride reacts with water, solution Y is formed that contains a complex aluminium ion Z and chloride ions. Give an equation for this reaction. This is worth 1 mark. So we just need to give the reaction, and that will be worth that 1 mark. So our aluminium chloride is AlCl3, and obviously our water is H2O. Now we are forming a complex aluminium ion, so these complex metal ions can support up to 6 water ligands, so we are going to need 6 water molecules here. Now, like the question tells us, this forms a complex aluminium ion, so this is going to be a hexa aqua ion. We are going to see that we have our aluminium followed by 6 water ligands, so H2O close bracket 6. Now this aluminium, like it says, is an ion. We can look at the oxidation state from the aluminium chloride to determine what the charge in this ion is going to be. Each of these chlorides has an oxidation state of -1. So for this to be a neutral compound, that aluminium must have an oxidation state of 3+. As each of these water ligands are neutral, they are not going to affect the overall charge of this ion. So as the aluminium has a 3+ oxidation state, the overall charge is going to be 3+. Finally, in our product, we have all of the chloride ions that were removed off of the aluminium ion. So we are then going to have 3 chloride ions. So we have, yes, our 6 water molecules substituting on to our aluminium ion as ligands, removing the 3 chlorine ions. We're going to need all of this for the 1 mark. Give an equation to show how the complex ion Z can act as a Bronsted-Lowry acid with water. This question is worth 1 mark. So the definition of a Bronsted-Lowry acid is that it is donating a proton. So what this question is asking us to do is show how the complex ion Z, which is our hexa aqua ion, hexa aqua aluminium ion, can donate a proton when it's reacting with water. So our complex ion is written as follows. It's our aluminium with 6 water ligands, which has a 3+ charge due to the ionization, or the oxidation state of the aluminium. Now we have this reacting with water, so we also need a water molecule there. And what we will see in this sort of situation is that the ion Z, our hexaqua-aluminium ion, acts as a bronzed laurie acid, as one of these water ligands will lose a hydrogen ion, it will donate a hydrogen ion to this water molecule. So what we will end up with is our hexaqua ion now only has 5 water ligands, but now has 1 hydroxide ligand. What this means for the complex ion is that because it has lost a hydrogen ion and this now has this hydroxide ion, this is actually a negative ligand. The hydroxide ion is negatively charged, so this reduces the overall charge of the complex ion by 1, so it's now a 2+ ion. That proton which it donated goes to the water molecule, forming a hydroxonium ion, that's H3O+. So to get this 1 mark, we need all of this equation, which shows that it can act as a bronzed laurie acid. However, we don't need any further justification for it. Describe 2 observations you would make when an excess of sodium carbonate solution is added to solution Y. Give an equation for the reaction. In your equation, include the formula of each complex aluminium species. This question is worth 3 marks. Those 3 marks are going to be split 1 mark for each observation and then 1 mark for the equation. We're going to start with the equation for this question, as we can use the products of that equation in order to deduce what observations we're going to get. Also in this equation, we are going to use the balanced ionic equation, as the sodium ions in the sodium carbonate solution and the chloride ions in solution Y are spectator ions which don't matter for the overall reaction. So, the reaction is between our complex metal ion, that's our hexaqua ion, so it's AlH2O6 with a 3+ charge, and our carbonate ions, that's CO3 2-. Now here we have a metal ion which we've seen is able to act as an acid, reacting with carbonate ions. And when carbonate ions react with acids, they neutralize them. So our metal ions are going to be fully neutralized, as it is an excess of sodium carbonate solution. So the fully neutralized form is when the charge has actually become neutral on the ion, when 3 of our water ligands have been changed. So we will see we have Al, H2O3, OH3, and that will be neutral now. As it no longer has a positive charge, it's no longer able to donate that proton easily, so it no longer acts as an acid. Furthermore, whenever we have a acid which is being neutralized by carbonate ions, that produces CO2, so that's our carbon dioxide, and it also produces water, so H2O. Now that we have written this out, we can start to balance the equation, and the first way of balancing it would actually be to balance it via the charges. As we can see on the right hand side, every compound is neutral, whereas on the left hand side we have 2 different ions. So we need to make sure we balance these to keep the charges neutral on both, to keep the overall charge neutral on both sides. Now we have a 3+ charge on our aluminium ion and a 2- on our carbonate ion. So in order to balance this out, we're going to need 2 complex aluminium ions to get a total of 6+ here, and then 3 carbonate ions to get a total of 6- here. So we have 6+ minus 6, so that's going to be neutral overall. Now that we've got that, we can start to use this to balance against the other side. So we can see we have 2 complex metal ions on the left hand side, so we're going to need 2 of these on the right. Additionally, we have 3 carbonate ions, so that's 3 carbon atoms, so we're going to need 3 molecules of carbon dioxide to balance that out. And finally, we are going to have 3 molecules of H2O. as a total of 6 hydrogen ions have been lost by the complex metal ions. So we need an additional 6 picked up by those water molecules. Now that we've got our equation, we can use it to start working out what our observations are going to be. The first is that this is no longer our metal ion. Now that it's lost 3 of its water ligands and they've become hydroxide ligands, is no longer going to be dissolved in the solution, as it's no longer charged, it's no longer soluble, and as a result we are going to get the formation of a white precipitate, which is our new complex metal compound here. Our second observation is going to be due to the production of our carbon dioxide, we are going to see effervescence, which is going to be because of bubbles of carbon dioxide appearing in the solution. So those are our 3 marks, our 2 observations, 2 for our observations, 1 each, and then 1 for our equation. Aqueous potassium hydroxide is added until in excess to solution Y. Describe 2 observations you would make. For each observation, give an equation for the reaction as it occurs. In your equations, include the formula of each complex aluminium species. This question is worth 4 marks. So we're going to get 1 mark for each observation and 1 mark for each equation. So to begin with this reaction, the first thing that's going to occur is we have hydroxide ions being added to solution Y. And what those are going to do is neutralize our complex metal ion. So like in the previous part, we are going to get a white precipitate formed of our new aluminium, our new complex aluminium species that is being formed. And it's being neutralized completely, so that's going to be 3 changes to the ligands. What we will see is that our aluminium hexaaqua ion, that's our H2O6, which is a 3+, is going to be neutralized by 3 hydroxide ions to produce, to cause 3 of our water ligands to lose hydrogen ions, so we get and form hydroxide ligands, so we get a neutral aluminium compound, which is going to be our precipitate. So that becomes Al H2O3 OH3, and those 3 hydrogen ions that have been lost from our complex aluminium ion are going to each join with one of these hydroxide ions here to form a total of 3 molecules of water. So observation 1 is white precipitate, it's going to get us a mark. Equation 1 is going to get us another of those marks. Now it comes down to what is then going to happen after this point. And the key to what's going to happen beyond this point is that the hydroxide ions have been added in excess, which means we can actually continue this reaction. So the hydroxide ions can react further, causing more changes to the ligands of this complex aluminium species. So we'll go even further from a neutral species to a negatively charged species. And this actually enables the aluminium species to become soluble once more as it's regained charge, so it's able to actually interact with the polar water molecules. And what this will do is that it causes the white precipitate that just formed to redissolve in our solution. As an equation, the way this occurs is that our neutral aluminium compound, our H2O, Al H2O3 OH3, is going to react with another hydroxide ion to form a compound where we have Al H2O2 and 4 hydroxide ligands, which is going to have a negative charge on it now. as though the charges on those hydroxide ions now overcomes the oxidation state of our aluminium at the center of this species. And that is going to produce another water molecule, as the way this occurs is this hydroxide ion draws off one of the protons on the remaining water ligands. So those are our 4 marks. First, a white precipitate is formed as the complex ion is neutralized, and then it redissolves as it reacts even further, forming a negative ion instead of the original positive hexaaqua ion. This question is about sodium and some of its compounds. Use your knowledge of structure and bonding to explain why sodium bromide has a melting point that is higher than that of sodium and higher than that of sodium iodide. This question is worth 6 marks. So when we have a 6-mark question like this, it is being marked on levels of response. And in order to get into the highest level of response and get the full 6 marks, these questions are divided up into normally 3 stages, which you must describe each of in a correct and complete manner. So in this question, our 3 stages are going to be, first of all, describing the bonding in sodium. Secondly, we're then going to describe the bonding in the sodium iodide and in sodium bromide. And finally, it's going to be comparing them and making a conclusion from it. So it's comparison and conclusion for our final stage. So these stages are quite common for this sort of question, where we're being asked to compare and explain 2 things. So it's always going to be stages 1 and 2 will be describing each of the things we're comparing, and then stage 3 will be comparing the 2 and making a conclusion from that. And in order to get into the top level of response and get all the marks for this question, we need to describe each of these completely and correctly. So we're going to start with describing the bonding in sodium. And when it comes to these first 2 stages, the way we lay out and the points we're going to make are going to be largely the same, in that, first of all, we want to describe the type of bonding that's present. So we're going to say that sodium has metallic bonding. Say it is a metal, so it has metallic bonding. After that, we're going to want to describe the structure of sodium. So we're going to say that it has a giant lattice structure. As again, that is the structure that we will get with a metallic element. However, we're not quite done yet, as there's always going to be about 3 points we want to make for each of these stages. So we've described we stated the type of bonding, we've stated the structure it has, but we also want to actually describe the bonding. We want to define what it is as to what actually bonds that element or compound together. So we said it has a giant lattice structure, and then we're going to say in which the metal ions are attracted to delocalized electrons. So those are our 3 points for stage 1. We've described and stated the type of bonding and stated the structure that the element has. Now that we've done that, we want to move on to stage 2, describing the bonding in sodium iodide and sodium bromide. And this is going to take the same form of structure to this. So we're going to start by stating the type of bonding. So sodium iodide and sodium bromide, as these are both sodium halide salts, so they are very similar in terms of structure and bonding. So we can talk about them together. They both have ionic bonding. So we stated the type of bonding. Next up, we want to state the structure. So they have a giant lattice structure as well. They have a giant lattice structure. So that's our second point for stage 2, stating the structure as well. As the question has asked to use knowledge of both structure and bonding, so we want to make sure we're mentioning both in order to be able to give a complete explanation of these. Now that we've stated the type of structure, we're going to explain and kind of define the type of bonding, so as to what ionic bonding is and how the atoms making up these molecules are actually held together. So they have a giant ionic structure in which there is electrostatic attraction. So that's a key term to be using when it comes to ionic bonding, electrostatic attraction. And this electrostatic attraction is between oppositely charged ions. So that there is the textbook definition of ionic bonding. It is electrostatic attraction between oppositely charged ions. And that there will give a complete explanation for stage 2 of this question. So now that we've described both the bonding in sodium and the bonding in sodium iodide and sodium bromide, we need to move on to comparing them and making a conclusion from this. So the first thing we need to state is how we're going to compare sodium bromide to sodium, because both the sodium iodide and sodium bromide are similar in structure, whereas sodium is different, so it's easier to start comparing them to the more different one first, and then talking about the differences between sodium iodide and sodium bromide. So what we are going to say is that ionic bonding is stronger than metallic bonding. So we will then draw a conclusion later to say that means that sodium bromide and sodium iodide as well will have higher melting points. But for now, that's all the only point we need to say about the comparison when it comes to between sodium and the sodium halide salts. Now we need to compare the sodium halide salts. So the key difference between sodium iodide and sodium bromide is in the halide ions. And while they both have the same charge, they're both -1 ions, the iodide ion, because it has more filled main levels of electrons, is larger than the sodium bromide ion. So that's going to be our first point. The bromide ion is smaller than the iodide ion. And then that's one point. We need to then actually explain what this means. Because the bromide ion is smaller, the sodium ion is going to be able to get closer to it. It'll get closer to the the sodium and the bromide ion will get closer together, which will actually increase the strength of the ionic bonding because they're closer together, so that electrostatic attraction between them is stronger. So the bromide ion is smaller than the iodide ion, so the ionic bonding in sodium bromide is stronger than in sodium iodide. So that makes up kind of the final point we need to make about the comparison. But we also want to give a conclusion to make sure we've got a complete answer. So finally, we're then going to say that therefore, sodium bromide has a higher melting point, as we want to tie this back to what the question was asking. So we need to make sure we are directly using phrases used in the question to make it obvious that our answer is directly related to the question. So sodium bromide is a higher melting point than both sodium iodide and just pure metallic sodium. And that will get us the full 6 marks of the question, as we have given a complete and correct description for all 3 of the stages involved in the question. We've described the bonding in sodium, we've described the bonding in sodium iodide and sodium bromide, and we've compared them and drawn a conclusion from that. When 250 milligrams of sodium were added to 500 centimeters cubed of water at 25 degrees Celsius, a gas was produced. Given the equation for the reaction that occurs, calculate the volume in centimeters cubed of the gas formed at 101 kilopascals. The gas constant R is equal to 8.31 joules per Kelvin per mole. This question is worth 6 marks. So what we will see from the 6 marks is that one of these is for giving the equation of the reaction, and the remaining 5 will be for calculating the volume of gas formed. Of those 5, 4 of those are going to be working marks, with the final one going for the actual value for the volume of gas. Now, we have the reaction that we're trying to find the equation for involves the reaction of sodium with water. So we can start by writing in our reactant. So we have sodium and we have water. Now, sodium, when it reacts with water, is going to produce sodium hydroxide. So that is going to produce sodium hydroxide, and that also is going to produce hydrogen, which is that gas which is given off. We then, however, need to actually balance this equation, as currently we have 3 hydrogen atoms on the right-hand side, but only 2 on the left-hand side. Now, there's two easy ways we could balance this. The first is that part of the reaction here, so from sodium to sodium hydroxide, leaves, for every mole of this which goes through, leaves 1 mole of hydrogen atoms left as the byproduct which goes on to produce this. So we can either make all of these so it's 2 moles, so that we have 2 moles of hydrogen atoms which can produce 1 mole of hydrogen molecules, or we can simply say that half a mole of hydrogen molecules are produced. Either is fine. Multiples are, as long as the equation is balanced, multiples are accepted, although generally we want to use the simplest multiples possible for an equation, so either 2, 2, 2, 1 or 1, 1, 1, a half is fine. Now we need to calculate the volume of the gas which forms at 101 kilopascals. The first thing we need to do for this, though, is to start calculating the moles of the moles of gas that are actually produced. We can't, without knowing the amount of substance that we have of a gas, we can't calculate what volume that will take up at a certain temperature and pressure. So in order to do that, we're going to use our equation with the numbers we were given at the question to start working out the number of moles of gas. So to begin with, we need to work out the number of moles we have of sodium. Now, moles is equal to mass over, in this case, AR, or MR if it's a compound. And in this case, we have 250 milligrams of sodium. So we need to convert that to grams. So that's going to be 0.25 grams. And our AR of sodium is 23.0. So that's going to get us a value of 0.0109 moles for our moles of sodium. However, that's not equal to our moles of gas produced, because if we look at our equation, for every 1 mole of sodium that reacts, we have half a mole of gas produced. So we actually need to divide this by 2 in order to calculate the moles of our hydrogen gas. So we're going to have 0.0109 divided by 2 to get us a value of 5.45 times 10 to the minus 3 moles. Now that we've got the moles of our now that we've got the moles of our gas, we can start actually working out the volume it's going to take up. Now, the ideal gas equation is equal to pressure times volume is equal to moles multiplied by the ideal gas constant multiplied by temperature. So we can see we're going to need to get pressure and temperature here. Now, let's start with pressure. The question told us that we have 101 kilopascals. However, we don't want the pressure measured in kilopascals, we need it in just pascals. So like converting between kilometers and meters, the way we're going to do this is multiplying by 1,000. That kilo means 1,000, so we just multiply by 1,000. So that's going to be equal to 101,000 pascals. We also need to work out the value for temperature, and that's been given to us as 25 degrees Celsius. However, once again, this isn't the unit we want. We don't want degrees Celsius, we need Kelvin. So we're going to convert that by doing by adding 273, so that would be 25 plus 273 Kelvin, which is going to be equal to 298 Kelvin. Now that we have all the quantities we need in order to calculate the volume, as we have every other quantity in this expression, with R was given to us in the question, we can rearrange this by moving the pressure over to the right. So we would get volume is equal to moles multiplied by the ideal gas constant multiplied by temperature over pressure. So now we can substitute in all our values. So we have 5.45 times 10 to the minus 3 multiplied by 8.31 multiplied by 298 divided by 101,000. Now that we've got that, we can put that into a calculator, which will get us a value of 1.34 times 10 to the minus 4 meters cubed. So this equation will always give us a value for volume in terms of meters cubed. So we need to then convert that to get our centimeters cubed, as the question asked for. So the way we're going to do that is by multiplying by 100 to the power of 3. So because converting from meters to centimeters, we multiply by 100. But because this is meters cubed, we need to raise that 100 to the power of 3. So we're going to have 1.34 times 10 to the minus 4 times 100 cubed, centimeters cubed, which is going to give us a value of 134 centimeters cubed. So that value of 134 will be our 5th mark for the calculation, 6th mark for the question overall. As for the remaining marks, they come all in the working. The first will be for working out the moles of sodium, the second for working out moles of our hydrogen gas, the third is for getting the correct values of both pressure and temperature converted from the units we were given them in the question to the units we need to use in our equation, and the fourth is for using the rearranged form of our ideal gas equation. So all in all, that's 6 marks for the question, 1 for the reaction equation, 4 for working, and 6 for our final value of volume. Calculate the concentration in moles per decimeter cubed of sodium ions in the solution produced in the reaction in question 8.2. This question is worth 1 mark. So in order to actually calculate the concentration of something, we need to use concentration is equal to moles divided by volume. And in the reaction in the previous question, we had sodium plus water producing sodium hydroxide and half a mole of hydrogen gas. And we calculated the moles of sodium, and we can see from this equation that that's going to have a 1-to-1 ratio with the eventual moles we'll have of sodium ions in this reaction. So what that means is that for this equation, our value for moles is going to be 0.0109, as it was in the previous part. When it comes to volume, however, we need to look elsewhere. The question told us that we had 500 centimeters cubed of water, so that's going to be the volume of our solution, so that's what we need to use for volume. However, that's in centimeters cubed, so we need to convert that to decimeters cubed by dividing by 1000, so that's going to be 500 over 1000 decimeters cubed, which is 0.5 decimeters cubed. So we have 0.0109 over 0.5, which is going to get us a value for concentration of 0.0218 moles per decimeter cubed. So that's the value that will get us our 1 mark. The fact it's only 1 mark means that we don't have any working marks, it's just 1 mark for our final value. Sodium reacts with ammonia to form the compound NaNH2 that contains the NH2- ion. Draw the shape of the NH2- ion. Include any lone pairs of electrons that influence the shape. Predict the bond angle. Justify your prediction. This question is worth 4 marks. So we can expect to see 1 mark for the drawing of the shape, including those lone pairs, 1 mark for the bond angle, and 2 marks for the justification of the bond angle. So drawing our shape, the first thing we want to do is draw in some square brackets and a minus sign here, as the square brackets show it is a molecular ion, with the charge being indicated in the top right here by whatever the charge symbol should be. Then we're going to draw our nitrogen atom that forms the center of this ion. And we now need to look at what the shape of the molecule is going to be. So we can see that this is formed from ammonia, and in ammonia we have the nitrogen atom has 3 bonding pairs and 1 lone pair. But now we've lost one of those bonding pairs, and this negative symbol indicates that that's because in doing so we've gained another lone pair. So what we can expect to see from this nitrogen atom is going to have 2 lone pairs and 2 bonding pairs. So that's going to give it a shape called a V-shaped molecule. So it's going to have 2 lone pairs, like so, and then 2 bonds with hydrogen atoms that give this V-shape, which is what gives the molecule shape its name. Then this bond angle we need to calculate from what it would be in a standard tetrahedral molecule, which is the standard for if we have 4 bonding pairs. But these lone pairs reduce the angle. So we have 2 lone pairs, and each lone pair reduces the angle by 2.5 degrees. In a tetrahedral molecule, it's 109.5 degrees. So we have 2.5 degrees being taken off twice. So as a result, that's going to give a bond angle of 104.5 degrees between these 2 bonds here. Now we need to talk about the justification for this. And the most important part of why this occurs is that, first of all electron pairs repel each other. But importantly, lone pair repulsion, so that's repulsion between two lone pairs rather than like a lone pair and bonding pair or two bonding pairs, uh, is the strongest electron repulsion. And on top of that, bonding pair repulsion is, that's repulsion between two bonding pairs rather than two lone pairs or a bonding pair and a lone pair, is the weakest of these, with lone pair, bonding pair in the middle between these. Now, what this means is that the electron pairs all repel each other. They all repel each other as much as possible. However, the repulsion between the lone pairs is greater than the repulsion between the bonding pairs. So that means that this repulsion overpowers the repulsion between these bonding pairs, which causes the bonding pairs to be pushed closer together. So these lone pairs are as far apart as possible, but these bonding pairs, while they're pushing back, are weaker, their repulsion is weaker than with the lone pairs. So they get pushed together, which ends up reducing the bond angle from that 109.5 degrees in a tetrahedral molecule where we don't have any lone pairs to this, well, 107 first and then 104.5 as we add lone pairs, and it pushes the bonding pairs closer together. So this question overall is 4 marks. 1 would be for the shape, 1 is the bond angle, and then in our justification, we'd get 1 mark for talking about how the electron pairs are all repelling each other, and the other comes from talking about how lone pair repulsion, when it's lone pair, is stronger than bonding pair repulsion. So those are our 2 marks for the justification. This question is about vanadium compounds and ions. Use data from Table 4 to identify the species that can be used to reduce VO2 plus ions to VO2 plus in aqueous solution and no further. Explain your answer. As we can see, Table 4 shows us the electrode half equations and the equivalent potentials for several electrodes from the 2 vanadium ions that were mentioned, as well as a chlorine electrode, an iron electrode, and a zinc electrode. This question is worth 2 marks. So we're going to have 1 mark for giving the species of reagent, and the second mark for explaining why that reagent is the correct one. Now, when it comes to reducing agents, the lower their electrode potential, the better a reducing agent they are, as they less strongly attract any electrons, as in order to be a reducing agent, they need to donate electrons in order to reduce another species. What that means is we need something that is able to reduce the VO2 plus ions here, but not the VO2 plus ions here. So that means we need something which is strong enough to reduce this electrode, but not this one. That means that we need whatever our electrode is to have an electrode potential between this +1 and this +0.34. Now, looking down our list of electrodes in Table 4, we can see that the only one that fits this is the iron electrode here. Now, before we give our reagent, we need to identify which ion of iron is the correct species as to which is actually the reducing agent. So we can see from this equation that the 3 plus ion is not the reducing agent, as it is itself being reduced, it's gaining electrons to form the iron 2 plus ion. What that means is that the 2 plus ion is our reducing agent, as it could, as we can see from the reverse of this reaction, that it would be able to donate electrons. So it is the reducing agent in this case. So the reagent is Fe2 plus. Now we need to explain it. And the reason this is the correct reagent is that it is able to reduce the VO2 plus, but not the VO2 plus, or the +1 ion, but not the +2 ion. So we need to write that in a way that actually explains it, because it was to do with the potential. So we're going to write it as an inequality and say that the electrode potential of our +1 ion was greater than the electrode potential of our iron electrode. So what that means is that shows that the iron is able to reduce that +1 vanadium ion. However, because the electrode potential of our 2 plus vanadium ion is even lower than that, it is not able to reduce the second vanadium ion, so therefore it is the correct answer. So we would have 1 mark for this reagent and 1 mark for this explanation. Give the oxidation state of vanadium in VOH2O5 2+. This question is worth 1 mark, so there are no marks for working or any justification, we just need to give the oxidation state. In order to work out the oxidation state of vanadium, we're going to need to look at the oxidation states of the other parts of the molecule and the overall charge of the molecule. So we can see, first of all, that we have 5 water ligands in this ion. Now, water is a neutral molecule, so this is giving us a total oxidation state here of 0. So the water ligands don't come into the oxidation state. However, we do have an oxygen atom here, and now oxygen atoms have an oxidation state of 2-. So what we can see is that we have an overall charge of 2+, and so far, out of everything else in the molecule, we have an overall oxidation state of 2-. So what we have is that the total charge plus 2 is equal to the oxidation state on the vanadium minus 2. So rearranging that, we would see that 2 plus 2 is equal to the oxidation state on the vanadium. So that's therefore going to be equal to plus 4. So the oxidation state of the vanadium in this molecule is going to be plus 4. And that would be all we need for that 1 mark. The VH2O4Cl2 plus ion exists as 2 isomers. 1 isomer is shown. Draw the structure of the other isomer and state the type of isomerism. This question is worth 2 marks. So the fact it's 2 marks means we are going to get 1 mark for the diagram of the other isomer structure and the other for naming the type of isomerism afterwards. So when it comes to complex metal ions, they can form isomers based on the placement of the ligands around it when we have multiple unique ligands. And in cases like this, we can have where ligands, these unique ligands can either be adjacent to each other or opposite each other. So we can see here that the 2 chlorine ligands are adjacent to each other. However, instead of that, and we can start to draw this out, remember we should keep our square brackets as it's still an ion in the other isomer. And we're still going to have our atom of vanadium at the center. But instead of, so if we draw 1 chlorine here, instead of the other chlorine being adjacent to it, it will be opposite to it. And then the same goes for our water ligands, who will now also be opposite each other. Rather than adjacent, as they were in the previous one. And this here, the difference between the adjacent ligands and opposite ligands, is what gives it isomerism, as these 2 compounds, while being very similar as their isomers, will exhibit some different properties. This, and in terms of what type of isomerism this is the same type of isomerism that alkenes exhibit around the double bond. This is known as EZ isomerism, which is short for entgegen zusammen, which is German for together and apart, or apart and together, even is the correct way around. They are also sometimes referred to as cis-trans isomers, although EZ isomers is becoming an increasingly common term. So those are 2 marks of the question, 1 for a diagram and 1 for the type of isomerism. Heating NH4VO3 produces vanadium 5 oxide, water, and 1 other product. Give an equation for the reaction. This is worth 1 mark, so we're going to get 1 mark for that equation. We don't need to give any justification or anything to it. When it comes to the reaction that's described in the question, though, something that's important to note is that it refers to it as heating, not burning. So this means that what we are seeing here is thermal decomposition, not combustion. Yeah. If it said burning, then it would be a combustion reaction. But it's just saying heating, then it's not a combustion reaction. It's just thermal decomposition, which means that all we are going to have as our reactants is just the vanadium compound, NH4VO3, as it's just this compound decomposing when it's heated to start producing these 3 different products. So we've been told 2 of our products, so we can start to write these in. And what we will see is, first of all, vanadium 5 oxide. So in order to find the formula for this, we need to think about the oxidation states present. So we have, this is overall a neutral compound, and the vanadium is at a +5 oxidation state. Our oxygen atoms are all going to be a -2 oxidation state. So in order to create a usable form of this compound, like a usable ratio between the two, we are going to need 2 atoms of vanadium, getting a total of +10 there, and then 5 atoms of oxygen, getting -10 to bring it back down to neutral overall. Then we've got water, which is H2O. And then we've been told we've got one other product. So if we look at what still hasn't been used from our vanadium compound, we can see we still will have some hydrogen and some nitrogen. We can also, before starting to write that out, see immediately that we're going to need to balance this equation, as we only have 1 atom of vanadium on the left-hand side, but we have 2 on the right. So we know there's going to be more nitrogen and hydrogen left after this. Now, a gas involving this means that we need a product which uses nitrogen and hydrogen, which is going to be ammonia, which is a very common gas, a very common gas containing both nitrogen and hydrogen. We can look to balance this. As we noted earlier, we've got 2 atoms of vanadium here. So in order to try and balance that, we're going to need to take 2 of our put a 2 in front of our vanadium compound. We can then start to look at the rest of our reaction and see if everything else balances out. So the vanadium bounces. Now let's look at the oxygen. We've got 3 by 2, so we've got 6 atoms over here. We've got 5 taken up in the vanadium oxide and 1 taken up in the water for a total of 6. Then we need to look at our nitrogen. So in terms of our nitrogen, we've got 2 on this side and only the 1 on this side. So it's likely we're going to need a 2. However, we should check the hydrogen as well before we adjust that. So we've got 4 by 2, so that's 8 on the left-hand side. Then there's 2 taken up here and 3 taken up here. So that gives us 5, which means we need an additional 3 hydrogen being used, which is what we would get with 2 the 2 in front of the ammonia on the right-hand side. So we can balance the equation by placing a 2 in front of the ammonia to get the final equation of our NH4VO3 producing vanadium 5 oxide, H2O, and 2 moles of ammonia. And that is what we need for the 1 mark for this question. Vanadium 5 oxide is the catalyst used in the manufacture of sulfur trioxide. Give 2 equations to show how the catalyst is used and regenerated. This question is worth 1 mark, which means we need both the equation showing how it is used and the equation showing how it's regenerated correct in order to get that 1 mark. Now, to begin with, we need to understand that sulfur trioxide is manufactured from sulfur dioxide. So our equation showing how it's used, what we will see for our reactant is going to be our catalyst, our V2O5, that's our vanadium 5 oxide, and sulfur dioxide, which is SO2. Now, we know this is going to form sulfur trioxide. What we need to understand is how it's going to do that. So this is going to be a redox reaction in which the sulfur dioxide is oxidized and the vanadium is reduced. So the vanadium will be reduced. So that's going to go from V2O5 to V2O4. It has both lost an oxygen atom and the vanadium has decreased from a +5 oxidation state to a +4 oxidation state. And that is going to, what we will see is that we have sulfur trioxide now. As the sulfur has been oxidized, it's gained the oxygen atom and also has gone from a +4 oxidation state to a +6. But that's our first reaction, how the catalyst is used. Now we need to show how it's regenerated. So this is a simple regeneration. All that occurs is that our V2O4 gains an oxygen atom in order to reform the V2O5. So what we will see is that we have our V2O4 plus 1/2 of a mole of oxygen molecules to produce our V2O5. Multiples are allowed, so you could also say 2 moles of our V2O4 plus 1 mole of oxygen molecules forms 2 moles of V2O5. But regardless, we need both of these equations to gain the mark for this question. A student added 627 milligrams of hydrated sodium carbonate, that's Na2CO3X H2O, to 200 centimeters cubed of 0.25 moles per decimeter cubed hydrochloric acid in the beaker and stirred the mixture. After the reaction was complete, the resulting solution was transferred to a volumetric flask made up to 250 centimeters cubed with deionized water and mixed thoroughly. Several 25 centimeters cubed portions of the resulting solution were titrated with 0.15 moles per decimeter cubed aqueous sodium hydroxide. The mean titer was 26.6 centimeters cubed of aqueous sodium hydroxide. Calculate the value of X in Na2CO3 X H2O, show your working, give your answer as an integer. This question is worth 7 marks. One of those marks is going to be for the value of X. The remaining 6 are all going to be for the working involved in this question. So questions like these where we have lots of numbers involved, the first step is always going to be to convert any non-mole amount of substances we have to moles. So using N equals C times V, so moles is equal to concentration times volume, in order to actually calculate the moles. Something to note though, those volumes should all be used in terms of their values in decimeters cubed. So if they are centimeters cubed, like in this question, we are going to need to convert those decimeters cubed by dividing by 1000. So to begin with, let's look at the moles of HCl. So the moles of HCl, our hydrochloric acid, are equal to 0.25 multiplied by 0.2. That's 200 over 1000. And that's going to give us a value for moles of 0.05 moles. Now we'll look at the number of moles in the average titer of sodium hydroxide. So the concentration is 0.15, and we have an average titer of 26.6 centimeters cubed, but that needs to be in decimeters cubed, so that's equivalent to 0.0266, which gets the value of moles at 3.99 times 10 to the minus 3 moles. Now, the next step is going to be to convert this, the number of moles that we needed to neutralize this portion of the excess hydrochloric acid, to the number that would be needed to neutralize all of the hydrochloric acid, all of the excess hydrochloric acid. Now, the way we need to look at this is that we were using 25 centimeters cubed sections of the solution in our titration, and the whole thing was 250 centimeters cubed. What that means is that if we were to do 250 over 25, that would get us 10. So we are working with 1/10 of our, we're working with just a tenth of the overall solution. So what we're then going to do is do 3.99 times 10 to the minus 3 times 10 to get 3.99 times 10 to the minus 2 moles. And this is equal to the total moles of excess HCl. So that is, our excess moles of HCl are equal to 3.99 times 10 to the minus 2 moles. As we've just seen, that would be the number of moles of sodium hydroxide needed to neutralize it, and as they react in a 1-to-1 ratio, it's going to be the same number of moles that we need to neutralize, it's going to be the same number of moles of the excess hydrochloric acid. Now that we have that, we need to work out the number of moles of HCl that actually reacted. So the reaction moles of HCl is equal to the total moles of HCl, which is 0.05, subtracting the excess, which is 3.99 times 10 to the minus 2, which is going to get us a value of 0.0101 moles that actually reacted with the sodium carbonate, the hydrated sodium carbonate. Now that we have done that, we need to work out the number of moles of sodium carbonate that reacted. And the way we are going to do this is by dividing by 2, as so our HCl and sodium carbonate react in a 2-to-1 ratio. So what we will see is that we need to divide the number of moles of HCl that reacted by 2 in order to get that. So the moles of our sodium carbonate, the XH2O there, is equal to 0.0101 divided by 2, which is going to get us a value of 5.05 times 10 to the minus 3 moles. And now that we've got that, we can start to actually work out the value of x. Because from here, the way we can do this is by working out approximately working out how much of the MR of the hydrated sodium carbonate, the hydrated part of that, the actual H2O, takes up. So what we're going to do is MR is equal to the mass in grams over the number of moles. So the mass in grams is 0.627, as we've been given it in milligrams, and we need to divide by 1,000 to convert it, divided by our 5.05 times 10 to the minus 3. And that's going to get us an MR for the hydrated sodium carbonate of 124.16. What we need to do then is work out the actual MR that the water is equivalent to. And the way we're going to do that is by subtracting the MR of sodium anhydrous sodium carbonate. So the MR of our sodium carbonate, we can find this by doing, so that the AR of sodium is 23. So we've got 2 lots of 23. Then we've got the AR of carbon, which is 12. So we've got plus 12. And then the AR of oxygen, which is 16. So then we've got 3 lots of 16. All of this together gets us an MR of 106. So we can then find the value of what's left of the MR as what is XH2O. So X by the MR of water is going to be the total MR, that 124.16, subtract the part of the MR, which is the sodium carbonate, so minus 106, which is going to get us a value of 18.16. So then we can find the value of X by doing 18.16 over the value of MR for water, which is 18. So we're going to have 18.16 over 18, which gets us a value for X of 1. So that is the final value of X, which would be 1 mark for us in this. However, the remaining 6 will come from the working, so let's identify where they all come from. So first of all, our first mark for the working is coming from converting both the hydrochloric acid and sodium hydroxide into moles. The second mark is then coming from calculating the moles of excess, the total moles of excess hydrochloric acid, with that 3.99 times 10 to the minus 2. The third mark then comes from finding the moles of hydrochloric acid that reacted. The fourth comes from the moles of sodium carbonate that reacted. And the fifth comes from actually just converting the milligrams of the mass was given into grams. And the sixth comes from actually getting the 18.16, finding the proportion of the MR, or what part of the MR actually the XH2O makes up, and then finally the 7th is for our final answer. So that gives us all 7 of the marks of the question. Only 1 of them is for the final answer. The remaining 6 are all working marks.